Hi everyone, let's do another one of these big examples where we crunch through and find critical values and classify and find inflection points and then sketch. So just to be clear, I am aware that it takes a really long time to do all of this. So on the test, you should be expecting to do bits and pieces. If I think I have enough room, I will have you go through the whole process with one function. But often I'll give you some first and second derivative information and ask you for a sketch, or ask you for the local maxes or mins, or just ask you for the maxes and mins and no sketch, or something along those lines. So expect me to give you some information needed for some part of this process, but not necessarily ask you to go through the whole thing for a whole bunch of problems on the test, because you would never get done. Okay, so let's go through one more big one. The reason I want to go through the whole process like this is because that's really the point, that you could put it all together and draw a graph, but again, it does take a long time. So first thing here, let's find critical values, which means we'll need k prime. Okay, so k is a quotient, so we'll need the bottom, x squared, times the derivative of the top. You could multiply that out, but now we've got a chain rule, so I'm just going to use it. We have stuff squared, which means the derivative will be 2 times stuff to the first times the derivative of stuff. But this is actually a nice one because the derivative of x minus 1 is 1, so that doesn't really make much difference. And then we have minus the top, x minus 1 squared, times the derivative of the bottom, which is a 2x. And that's all going to be over x squared squared, which is x to the 4th. Okay, so I should point out here, a lot of times what we would do is multiply all of this out. And we could do that here, but I think that my advice would be to, if you can spot it, do some factoring instead. Look, we have this separated into 2 terms, and each of the terms has an x minus 1. We can't get both of them, but we can get one of them. Each term has a 2, and each term has an x. Again, we can't get both of these, but we can get one of them. So if we factor out the 2, the x, and the x minus 1, what we'll be left with is a single x here, the 2 and the x minus 1 are gone, and then minus an x minus 1 left over here. Okay, and then this, do I have colors? Okay, so this becomes x minus x plus 1, which is actually just 1. So this doesn't need to show up, it's just times 1. We can cancel out one of the x's. So what we really end up with is that k prime of x is equal to 2x minus 1 over x cubed. So that actually simplified really nicely. So if we're looking for critical values, the critical values are going to be, when is k prime 0? And the answer is k prime is 0 if x equals 1. And then when is k prime undefined? And that would happen if x equals 0. But again, whenever you have those, double check. So if x equals 0, the function is not defined as well. So that might be interesting for a sign chart, but it's not a critical value. So we only have one. Critical value is at x equals 1. One and only. Okay, so now we're supposed to classify the critical value using first and second derivatives. Again, on a test, I'll probably ask you for specifically first and second derivative tests on different problems. I might leave it open on some as well so that you can show me that you make a good choice about that. But be prepared to show me either one. Don't just practice one. Here we'll show both so that we can compare again. Okay, so if we're using the first derivative test, we're going to start our sign chart with the critical value x equals 1. And I am going to show, it's not a critical value, right? But I am going to show that the derivative is undefined at 0, because otherwise I might not have great information. I might not have the right information here. Okay, so critical value, so 0 here. So this is my only critical value. Okay, so this one actually is a great example. If you forget to put 0 on this chart, you might either be trying to plug 0 in, which will give you undefined, or you might plug in something over here, which isn't close enough. The derivative could change signs at 0, so we need to plug in like 1/2 would be a good choice, and 2 would be a good choice as well. So when x equals 1/2, here's my simplified derivative. I get 2 times negative 1/2, which is negative 1, over 1/2 cubed, which is positive 1/8. So the derivative is negative at 1/2, which means function is decreasing. And this is derivative information, but I am showing pictures. And then we have a flat spot at 1. And then if we plug in 2, we get 2 times 2 minus 1, which is 1. So that's positive 2 over 2 cubed, which is 8, positive 8, which means the derivative is positive and the function is increasing. So that tells me that there is a max at x equals 1. Oh, what is with me saying them backwards? I just drew it very clearly, and it is a min at x equals 1. Don't mind me. Okay, so that was a first derivative test, done. For the second derivative test, this is actually another example of when I think the first derivative test would be easier, but trust me when I say that it's not always. Sometimes the second derivative test is really quick and painless. Here it's just looking a little messy because I'm going to have to do another quotient rule. So I'll take the bottom. The derivative of the top, we could even multiply this out. So it's 2x minus 2. The derivative of the top is just 2. Minus the top, 2x minus 2, times the derivative of the bottom, 3x squared. And this is all over x cubed squared, which is x to the 6th. So this isn't really terribly bad, but it does seem like I'm going to end up going through a little bit more work. Okay, so I have a 2x cubed minus, let's see here, minus 2x times 3x squared. So minus 6x cubed, and then minus plus 2 times 3x squared, so plus 6x squared. So k double prime is equal to 2. So 6x squared minus 4x cubed over x to the 6th. And I could factor out a 2x squared. I'm going to see what that looks like. I'd be left with a 3 minus 2x. But I don't think it helps me, at least on the test. I don't think it helps me on the second derivative test terribly. So you can, or, oh, actually I lied. I do like it because look, I can cancel out some x's. So I'm going to say I have 2 times 3 minus 2x over x to the 4th. Okay, so now, and again, make sure you're really thinking about this. Second derivative test, you plug in the critical numbers, not numbers on either side, but the actual critical numbers. So that was just 1 in this case. And I get 2 times 1 over 1, which is just 2, which is telling me that at the flat spot, the function is concave up. Please show me something along the lines of just a quick sketch so I know that you really were thinking about second derivatives. Okay, so let me say it right this time. So this is a local min at x equals 1. My brain keeps wanting to say max there. Okay. Last part is to find inflection points and then try and do a quick sketch of this thing. So inflection points we're going to find by setting the second derivative. So actually this is another reason that it was kind of nice to simplify, equal to 0. And that will happen only if the top is 0. So it looks like x has to be 3 over 2. Okay, so we have one potential inflection point, 3 over 2. Again, it might be good to note that the second derivative is undefined at x equals 0. So when we go to check on either side, we want to pick something between 0 and 3/2. Okay, so f double prime x. Okay, so I'm going to try 1, and I'm going to try 2. Okay, so when I plug 1 into the second derivative, did we already do that? We did. We got 2, which is positive. And when we plug 2 into the second derivative, we get 3 minus 4. So negative 1 times 2, which is negative 2, over 2 to the 4th, which is 16. So we get negative 2 over 16. Which is definitely negative. Okay, so we did change from concave up to concave down. The function changed from concave up to concave down. So that is an inflection point. There's an inflection point when x equals 3/2. Okay, so putting this all together to sketch, let's see, I have, these are kind of my key, where's the highlighter? Key things here. We have this information and we have this information. So I might even summarize some of the above stuff so it's all in one chart. So I know that the second derivative, okay, so 0 is key for both of them. Okay, so there's an asymptote at 0. I hope that that seems fair for me to do that. Whoa, I have autofocus on and it is blurry. I hope it hasn't been the whole time, you guys. Please get into focus. There, let me shut it off. There we go. Okay, so I know that my original function is k of x equals x minus 1 squared over x squared. So I know that there is, in fact, a vertical asymptote at x equals 0. That's when the bottom is 0. And then I also, if you remember, can figure out that whole global behavior thing. That's really helpful when you're trying to sketch. So if x is a really big positive number, say it's like 1,000,000, I have 1,000,000 minus 1 squared, which is awfully close to 1,000,000 squared, divided by 1,000,000 squared. And the same thing happens when I plug in negative 1,000,000. I have negative 1,000,001 squared over negative 1,000,000 squared, which is really close to 1. So it looks to me like I have a horizontal asymptote at y equals 1. And then, okay, so that was original function stuff. Let's see, the second derivative. Now, let's do first derivative next. So the first derivative, we have a critical value at x equals 1. And we decided that it was a minimum. So we know that the derivative goes, let's see, at x equals 1, it's 0. So this is f prime up here. At x equals 1, it's 0. It's negative in the middle here. It's positive forever after. And just because I need to draw this side as well, I'm going to go back to the derivative right there and say, okay, what if I plug in negative 1? So I get negative 2 times 2 is negative 4 over negative 1, so it's positive back here. Okay, so the function goes increasing until we hit the asymptote, and then it's decreasing, flat, increasing. And then the second derivative is positive everywhere between the asymptote and the inflection point at 3/2. So this is our IP, and then it's negative forever after. And same thing there, for sketching purposes, I'm going to plug in a negative number 2. So at negative 1, here it is. At negative 1, I get 2 times 5. So 10 over negative 1 to the 4th, which is positive. So it's concave up over here as well. Okay. So if I want to put that together, I should have left room underneath. I know that at x equals 0, I have a vertical asymptote. At y equals 1, I have a horizontal asymptote. At, let's stare at the original function a little bit more. When x equals 1, my y value is 0, so it goes through 1, 0. Okay, and let's see what else we can get here. So we know that to the left of the vertical asymptote, the function is increasing concave up. We also know that it starts off really close to this asymptote. So starting from here, if we have to go increasing concave up, I think that's the shape we can get. You can plug in numbers if you want a little bit, but we should have a general idea of how to sketch rationals anyway, so we get some free information. We know that between the asymptote and the critical value, which we decided was a minimum, the function is decreasing concave up. So decreasing concave up looks like this. Decreasing concave up. And then there's a minimum at 1, 0, and it switches to increasing concave up, but not for very long. At 3/2, we have an inflection point. So at 3/2, it switches from increasing concave up to increasing concave down. and then it stays that way forever. So I think that's just the downward bend that's going to bring us closer and closer to that horizontal asymptote. So there is a decent sketch of that one. Thanks for watching.